So now that we've addressed increasing and decreasing, the next topic of discussion is what we call extrema. Now, to begin with, extrema is just a fancy name of saying maximum and minimum. All right, so when I say extrema, I'm talking about a max and I'm talking about a min. But it turns out that there's actually two different types of extrema. Sometimes they coincide, but generally they are different. So a local extrema, what this basically means, this is a max or a min, depending on the issue. It's a max or min in a part of the domain. And the one thing that happens in a local extrema is it happens either at the top of a hill, that would be a max, or it happens at the bottom of a valley. And so what this also means in relation to this, local extremas, if I'm at a hill, that means I'm on my way up, and then I basically go on my way down. So that's how we create a hill. We go from increasing to decreasing. So I'm at the top of the hill, local extrema, in this case a local max. To be a minimum, right, what would have to happen is I would be decreasing, hit that low point, and then I would be increasing. And so we're basically at the bottom of a valley. So what distinguishes local extrema from absolute extrema is this action. I can increase up and then go down to be at a max, local max, or I could be going down and then up to be a local min. So that is one distinguishing feature about a local extrema. It will always happen right at a hill or a valley. So before we talk about absolute extrema, let's go ahead and now that we have a definition, if you would, for local extrema, let's go find them for the graphs. Okay, so unfortunately, I think I mistake when I put this together. We've already handled the increasing and decreasing, right? So let's just go ahead. When we're increasing here, we're on our way up, and then we're on our way down, so we're at the top of a hill. So technically speaking, right, we have a local max, and that local max is occurring at -3, 4. So this is a point. It's not the increasing and decreasing action were intervals of action, but extrema is occurring at a particular point. So -3, 4 is basically at the top of the hill. In this particular graph, there is no local minimum, right? Because this is going to go downwards forever, and this is going to go downwards forever. So we technically never hit a valley, right, where we go down and then back up. So this particular graph has no local min, but it's got one nice local obvious max. It's got a hill. The next one, we kind of reverse ourselves, right? We go from decreasing to increasing. So what I have here is a valley. So my local max, or excuse me, my local min would be occurring at 0, -4, because at this location is where I'm at the bottom of the valley. We go from we change from decreasing to increasing, so we're at a valley. This would have no local max because there's no hills, right? This is going on forever, and this is going on forever. So I never have that action where I'm coming up and then going down. There's no hills, so there's no local max. There's one valley, so we have one local min, and so forth and so on. So the next graph, right, we're looking at this, and I see that we've reached a high point right here, right? We went from increasing to decreasing. So that is what we call a local maximum. It looks like it's occurring at -2, and how about we just say 5.5, right, to be good enough for government work. And then this, right, we go from decreasing to increasing, we're at a valley. So this would be a local minimum, and that would be occurring, it looks like at -2, how about we say, or +2, and -5.5, just to be a rough estimate. So again, extrema are points on a graph. Local extrema, max or mins, maximums occur at tops of hills, and minimums occur at the bottom of valleys. Or said another way, we go from increasing to decreasing, top of a hill, or we go from decreasing to increasing the bottom of the valley. Local extrema. This particular graph we've already mentioned, it's always decreasing. So since it's always decreasing, we're never really at the bottom of a hill, or excuse me, at the bottom of a valley, or we're never at the top of a hill. So this would have no local extrema. It has no local maximum, no hill, and it has no local minimum, no valley. Okay, so that is local extrema. You got to be at the top of a hill, or you got to be at the top of a valley. We're at a high point in some part of the domain, right? Or we're at a low point in some part of the domain. The absolute extrema, don't confuse that with absolute value, because that's what we're talking about here. But this is basically the max or the min over the whole domain. So we're now, rather than considering parts of the domain like local extrema, we're talking about for the entire domain, this is your highest point. Or for the entire domain, this is at your lowest point. So it is truly the highest value for everything within the domain. There's no other higher output, or there's no other higher or lower input. So looking back at this, let me even go back to change colors here. This point, not only does it serve as a valley, not only does it serve as a hill, making it a local max, but it also serves as our absolute max, because that value of 4 is the highest y value for every value of x along the domain. Everybody's lower than that. And again, there is no absolute minimum, because we are going towards negative infinity in both directions. We never actually reach that lowest point. So an absolute max or an absolute min have to be reached. Here we do reach that highest point, but because we're always decreasing or going downwards, a downward motion, there's no absolute min that occurs. Over here, again, we have, this is the lowest value throughout the whole domain. So not only is this a local min, but it's also an absolute min. It's occurring at 0, -4, because that happens to be the lowest y value for everything throughout the domain. And because we're going to infinity in both directions, right, there is no absolute max here, right, because we never reach a highest point. We're constantly getting higher and higher and higher. For this graph, there were a couple of mins, right, extrema. A local max was occurring at this hill, and a local min was occurring at this hill. But because we're going to positive infinity here, and because we're going to negative infinity here, this graph would have no absolute extrema. There is no highest point that we reach. There is no lowest point that we reach. We're constantly going bigger and bigger and bigger, positively or negatively. So again, we never reach that highest or the lowest value over the whole domain. It's unbounded, basically. And then again here, there really isn't, again, this is going upwards to infinity, and this is a really weird case. It's getting closer and closer to 0, but we never reach 0. And we're getting back, it's called Zeno's paradox, actually. 1/2 and 1/3 and 1/4 and 1/5 and 1/10, 1/100th, 1/1000th. All those fractions are getting closer and closer to 0 without ever actually reaching it. So this guy would have no absolute minimums or maximums as well. No local, it has no local extrema and no absolute extrema, because we never reach, we'll never reach infinity, and we actually never reach 0. I can get as close as I want to 0. 1 in 1 millionth and 1 in 1 gazillion trillionth, right? There's always going to be some little gap that doesn't make me equal to 0. And in order to be an extrema, I have to be able to assume the value. Again, locally, I have to reach the top of the hill. I have to reach the bottom of my valley. For the absolute extrema, I've got to be the highest value that's reachable, right, for everybody. I've got to be the lowest value that's reachable for everybody. Otherwise, if you can't reach that value, then you are not in extrema. Again, there's so much more math behind this, but we're just going to do what the book's asking us to do, approach it very visually, and we're basically looking for hills and valleys for local extrema, and we're looking for largest values or smallest values over the entire domain for absolute extrema. Okay, so much more to this. We'll keep on building.